Alright, so in this video we're going to continue on with this final exam question that I've asked, and in particular we're going to calculate the back stress for our stress step. We're going to do this in two ways. We've already taken this big step in stress. We calculated the elastic part of it and then the elastic plastic part of that stress step. And we're going to go back and we're going to calculate where that back stress should be based on what our known radius should be in deviatoric stress space. And then we're going to do the same thing, except we're going to do this incrementally with Prager or Ziegler hardening. So let's just kind of review schematically what we're talking about, and then we'll take a look at some numbers, and then we'll take a look at the spreadsheet again. All right, so in the previous problem, and let me look up those stress numbers here. Let me write that matrix down. We started off with initially zero stress, and we went to the stress tensor values. I'm going to write down here, these are in megapascals. 400 minus 450 in 186, and 200, 0, and 80, and that's symmetric. Okay, so we went from sigma is equal to 0 to this big stress step. And what we did is we converted this to deviatoric stresses. And again, just to write this down, the formula for that is sigma ij minus 1/3 sigma kk Kronecker delta ij, where we have the implied summation with this double subscript here. Alright, so we went to do that, and we expressed this in stress space. And in stress space, the yield criterion makes the form of a circle, or a hypersphere, actually, in 9-dimensional stress space. We're going to express this as a vector, and the vector that I've been writing it is, I've been going across each row in this manner. Now there's different ways to order this, but I've been writing this in this manner, and the accompanying deviatoric stress vector as well. Now this being in deviatoric stress space, we can do this in either regular stress space or deviatoric stress space. There are certain advantages of working with deviatoric stress space, and that's the fact that we do get the hypersphere for the J2 criterion. And just to write down J2 again, it's 1/2 Sij. Again, we have the summation notation. And if we want to set this criterion equal to 0, that's when, let's see, 1/3 of sigma naught squared is equal to 0. Or we can rearrange this term right here, and oftentimes you'll see me write it like this. Sij is equal to 2/3 sigma naught squared, where this is our initial yield stress, and for this particular problem I had stated that was going to be taken as 150 megapascals. Alright, so we were at 0 stress and strain. We had this big excursion in deviatoric stress space, and we landed maybe out here somewhere. And that corresponds to the stress that we get from this deviatoric stress right here. We made an elastic jump to here, and then we incremented this in increments in stress space, deviatoric stress space of ds, or in regular stress space d sigma, and we calculated the plastic strains based on the normality flow rule, and we said that the elastic total strains is equal, the total strains are equal to the elastic strains plus the plastic strains, and these are tensor quantities. All right, so for each delta sigma is what we ended up taking, because we need to do a finite but small increment. We update our stress state, our strain state, to be the previous strain state plus our change in strain. And then we do the next step, and so forth and so forth. And we showed all those details. Okay, so now we're out here, and now let me show this in a different color. Now we're sitting out here, and our yield surface is on this path because we had a proportional path. In a deviatoric stress space, we know the radius of this yield surface. Since this is r squared over on this side, r has to be the square root of 2/3 times sigma naught. So if we want to calculate the location of the backstress tensor, which would be, use a different color, from the origin to here, it's supposed to be a straight line. Well, we can find out that then alpha ij, talking about the deviatoric alpha, is equal to S minus R, but that's a scalar. So what we really want to do is we want to take and go minus R times a unit normal in the direction of S. Okay, and so that's what we're going to do in this next step. Alright, so let me grab my spreadsheet. This is a continuation of the previous one. And so what I have in here are my stresses and my deviatoric stresses. And I need to find the unit normal that's in the direction of this deviatoric stress vector. Okay, so I'm taking the magnitude of this. Of course, the way you find the magnitude is the square root of the sum of the squares. It's 9 dimensions, but that's fine. It works the same way as any other magnitude for a 2 or 3 dimensional vector. And then this is my unit normal. And I just did a check right here just to make sure that the square root of the sum of the squares of those terms add up to be 1, and it does. Okay. Now here's my radius term, square root of 2/3 times 150. And so this expression right here is S minus R times that unit normal. Okay, just like we talked about. And so that's this term here. So these are the locations. This is the location of the back stress with respect to the origin of deviatoric stress space. These components, and they have the same, X, Y, Z, whatever components that we had over here. Let me just copy this over here to make sure that this is clear. Okay, so those are those components. All right, so you can only do this if you have a proportional loading path. You can't do this if you have a non-proportional loading path. So what I mean by a proportional loading path is we need to be starting from the origin of stress space and have a straight shot out. If it's a curved path, if you're not starting from the origin, you can't do this. You have to use an incremental approach, or you have to be careful and use a different kind of closed form integration approach. Okay, so we're going to check these numbers based on what we get based on applying the Prager-Ziegler hardening rule. So let's see if I have enough room to write a little bit of this in here. So we wrote last time that d alpha was equal to d mu times S minus alpha. And this d mu had to be determined by what we call the consistency condition. Now previously we had written it this way, and I'm going to write it just a little bit different this time. We had written it as partial of f with respect to S, maybe mn, maybe I used dsmn. Those are dummy indices, they're repeated, divided by partial f, partial s KL, and then we had SKL minus alpha KL. And ordinarily this is fine, except our yield function isn't really, we don't really want to take a partial of that with respect to SMN unless we're doing isotropic hardening. Really what we want to do is we want to take the partial derivative of our yield function with respect to xi. So in general, we can say this is true before we start moving our backstress. I guess specifically we can say this is true until we start moving our backstress. But once our backstress starts moving, this expression has to change a little bit. Our expression for our yield criterion is really xi ij is equal to 2/3 sigma naught squared, where xi is equal to s minus alpha, the location of the backstress. And that's because we're saying in our kinematic hardening model, pure kinematic hardening, our yield surface radius doesn't change. So really our function f that we're going to end up using then is going to look like this. And then when we evaluate this partial derivative, we have to be a little bit careful. Really what we want is the partial derivative of f with respect to xi mn dsmn, that's fine, and the partial derivative of f with respect to xi kl skl minus alpha kl. Alright, let's make a little bit of room and let's talk a little bit more about that. Alright. Now this consistency condition can be expressed instead in terms of regular stress space. Then you'd have a d sigma mn and you'd have a sigma kl minus alpha kl, where alpha kl is the back stress in the regular stress space. What I'm going to do next is going to be kind of specific to the J2 criterion. If we look at the functional form then that we just wrote down, we said f was equal to xi ij minus 2/3 sigma naught squared. If we take the partial derivative of this function f with respect to xi mn, well, what we're going to get, we have each of these terms squared. Okay, so basically what we're going to have is we're going to have 2 xi mn for this term. So in our specific case, d mu is going to be equal to xi mn times 2 the smn divided by 2 xi kl, and this term right here is also xi. Alright, now those 2's will cancel out. And we have this term down here. Now the interesting thing to note is we know what the value of that is. That is this term right here. It's 2/3 sigma naught squared. So as long as our yield surface size doesn't change, we can replace this with just a constant because we know what that size has to be. Alright, so let's rewrite this again. D alpha ij is equal to d mu, and then we had s. We're writing this in deviatoric stress space. Sij minus alpha ij. Alright, so let's take a look. We're starting out at the origin. We made a big jump over to here, and now we're going to have a loading increment. We'll talk about loading and unloading in the next video. We're going to have a loading increment. Right now our alpha is 0, but we're going to update it. Alpha new is equal to alpha old plus d alpha. And we keep doing that until we finally get to where we want to be, the end point of our stress change. Again, in this case, in deviatoric stress space. Alright, so now we're ready to look at the incremental process, and we'll see what numbers we get. Alright, so let's go here to incremental. Okay, so this is the same spreadsheet that I had previously. And it says look over here to the right. Now I did notice one issue I had in the spreadsheet last time. Remember I said that I didn't need the dV torque stress last time, or the dV torque stress increment last time. But I had put that in there anyway. Actually this set of values was in error. What I really need to do is these are going to be constant, so I'm going to take my increment divided by 100, and those are going to be based on my change in stress. See if I can find it. Should be these terms right here. It's based in my change in stress divided by 100 because I'm using 100 increments. So let's see if we can just double check that real quick. And in general, watch out for any errors that might be in here. I'm not going to promise that this is absolutely correct in every case here. Alright, so let's see. What we want to make sure is that we have the right value for our deviatoric stress increment. So here is my stress that puts me on the yield surface. And what I really want though is the remaining stress. Let's see if I can find it. Okay, so this is my delta, and this is this by 100. So my deviatoric stress increment I calculated based on my stress increment. Okay. So that's what I did. I didn't do a separate amount. So let's go back and look at our sketch again. Make sure we understand where that's coming from. Okay, so I'm calling this like my delta S, which corresponds to my delta sigma. What I've done is I'm calling my D sigma, my delta sigma divided by 100, and then I have a corresponding ds. Alright, so that's what that's all about. Alright, now I have my deviatoric stress increment. Let's kind of go over here. We talked about calculating plastic tangent modulus and the strains. Let's see if we can find our alphas. Okay, here it is. Here's my alpha. It starts out at 0 for all of these terms. Here is my xi, which is equal to S minus alpha for all of those terms. Here's my d mu term. It's a big long equation, but it's just what I had written before. Xi dot ds over xi dot xi. And here is my increment for d alpha. Alright, now my alpha is going to get updated by adding the previous alpha plus the increment. And we're going to do this till we reach the end of our 100 increments. That should be this number down here. So let me write a couple of these down. 292.2, 164.8, 0. I'm going to write them down this way as a vector, since maybe I can get some room here. I guess it's about as good as I'm going to get. 164.8 minus 408.1, 65.9. 0 and 65.9. Finally 115.9. Alright, let's go back to that other spreadsheet and let's check to see if we got the same thing. $292, 164, 0, 164 minus 408, 65.9, 0, 65.9, 115.9. Alright, so either way, either incrementally or by doing this single step in calculating the backstress where it needs to be along that vector will work. In general, you'd want to use the incremental approach. In certain circumstances, like I said, you get away with calculating the whole thing in one step. Alright, so what we're going to do for the next video is we're going to go to another state of stress, and we're going to figure out whether or not we're loading or unloading, and we'll find out where our backstress is going to end up after that step.